So in this lecture we will discuss the orbital picture of Diels Alder reaction, then some reactions regarding stereoselectivity and regioselectivity. So first of all we will discuss about the orbital picture, like this is your diene. When it combined with the dienophile, you will get this cyclohexene. So this is the very basic reaction of Diels Alder, and this reaction is also known as 4+2 cycloaddition. 4 pi electron plus 2 pi electron, this is called 4+2 cycloaddition. So how will you draw the orbital picture? Like in case of this alkene, okay, so in alkene there are two carbons which are forming the carbon-carbon double bond. Like simply we discuss that CC, and this is the structure of ethene. Okay, so all the 6 atoms, 2 carbon and 4 hydrogen, they are in one plane. So now each carbon is sp2 hybridized, so it has one p orbital like this. So this is positive low, so make it like this. So when positive overlap with positive, negative overlap with negative, it's bonding molecular orbital. So another way, this orbital may be negative overlap with positive, positive overlap with negative, so it form another. So these are the two atomic orbitals. They combine, give rise to 2 molecular orbitals. So when you study the molecular orbital theory, so in case of ethene we get this 1 and 2. So this is your you can say bonding molecular orbital, it's called psi1, and this is your anti-bonding molecular orbital, plus combined with minus. Okay, so there is 0 node and there is a 1 node. Similarly, when we have a 1, 2, 3, 4 p orbitals, so 4 p orbitals means they will give 4 molecular orbitals, 2 bonding, 2 anti-bonding. As we study in the molecular orbital theory, that the number of molecular orbitals equal to the number of atomic orbitals. So there are 1, 2, like we just give the numbering. So 4 molecular orbitals, they combine to give a 4. You can say these 4 atomic orbitals, they give rise to 4 molecular orbitals. So 2 are bonding, 2 are anti-bonding. Like this we have drawn this like structure. So first is like these are the 4 atomic orbitals, 1, 2, 3, 4, like 1, 2, 3, 4. So all having positive lobes, overlap with positive lobes like this. Okay, so this dark means positive, so this is your psi1. So this corresponding to 0 node. No node is there. Now we have another orbital in which this is a second molecular orbital. So it involves the overlapping of 1 with 2 and 3 with 4. Okay, so there is a 1 node. So this is known as psi2. This corresponding to 1 node. Now next is we are drawing psi3. This is actually anti-bonding, so put a star here. Okay, like this is psi1, this is psi2, put a star over here. This is anti-bonding. So here we have 2 nodes. Okay, 2 nodes means this corresponding to this and positive lobes below, and here is, so this is 1 node, this is another node. So 2. Now we have a psi4, this is also anti-bonding. So this corresponding to 3 nodes. This corresponding to 3 nodes, like this is positive, this is positive, here this is positive, and here again this is positive. So this 1, 2, 3. So now in this diene we have a 4 molecular orbitals. Okay. So there are only 4 pi electrons, 1, 2, 3, 4, and these 4 electrons are filled like this. And in this diene we have only 2 pi electrons, and these 2 pi electrons are filled like this. Okay. Now this is its highest occupied molecule. This orbital is known as a HOMO, HOMO. That is known as highest occupied molecular orbital. Highest occupied molecular orbital. And this orbital is known as LUMO, LUMO. LUMO means lowest, U means unoccupied molecular orbital. Okay. So highest occupied, because this diene, we know that this is nucleophile, and this is your electrophile. So this nucleophile has to donate electron to electrophile. So its highest occupied molecular orbital, which has a 2 electron, that combined with the lowest unoccupied molecular orbital of dienophile, which is empty, then only the bond is formed. Okay. So let's see how this overlapping is possible under thermal conditions. Okay. So this is LUMO. So HOMO of this diene combined with LUMO of dienophile. So just take this HOMO of diene. Okay. So you just make a structure like this. 1, 2, 3. This is of dienophile. This diene. Okay. So this is highest occupied molecular orbital. So you put here positive lobe. Okay. Then we have a downward positive lobe like this. Then we have a upward positive, and like this. And then we have this is, I think, I just put a wrong here. This node here, positive, 1 and 2 nodes. Here must have this orbital. Okay, this must be dark. Okay, there is only one node. So and this is like this, and this is here. So there is one node only. There is one node. These two are positive. These two are positive. So there is one node. So now in the last we have this orbital filled. So like this. So this is HOMO of your okay. Now there is again a problem. No problem here. There is a one node here. So this is HOMO of diene. Now what is LUMO of this dienophile? This is the LUMO of dienophile. So you can write like this. This is LUMO. Okay. So this filled up this one, and here filled up this one. Okay, now this is HOMO of diene, this is LUMO of this dienophile. So positive overlap with positive, negative overlap with negative. So there is a perfect overlapping between the negative with negative and positive with positive to form this. Now how this bond is formed? This bond is formed by rotating these, because there is a single bond, and when these two orbitals rotate, they form a double bond here. Okay. So this is the orbital picture of this Diels Alder reactions. So diene has these 4 molecular orbitals. 2 are bonding, 2 are anti-bonding. In bonding we have 0 node, means all the positive above, and in 1 node we have 2 positive below, 2 positive above. So there is 1 node inside. So in the 2 nodes we have up positive then down positive, up positive, like this. So in this dying we have 4 electrons, so 2 are filled in psi 1, 2 are filled in psi 2. So this psi 2 become a HOMO. HOMO means highest occupied molecular orbital. And in case of this dinophile, we have these 2 molecular orbitals because it has only 2 p orbitals. Either the positive overlap with positive or positive overlap with negative. So we have bonding and anti-bonding. This psi 1 is bonding and this psi 2 star means anti-bonding. So this is your nucleophile, so it has to give electron to electrophile. So it's highest occupied molecular orbital that going to combine with the lowest occupied molecular orbital of dinophile, like this. So overlapping is okay. So that's why this reaction is, you can say, is a thermally feasible. Okay, thermally allowed means when you heat, this reaction is allowed. Now, next is about the stereoselectivity. So let's take some examples about the stereoselectivity Diels Alder reactions. So suppose we have this diene and it combined with the dinophile carrying 2 electron. W means withdrawing group, electron withdrawing group. So this dinophile is this. So when you heat, what you get here is, just give the numbering as we explained previously. So you get 6 membered ring. Again give the numbering 1, 2, 3, 4, A and B. So where these W are attached, they are cis. So they are cis to each other. So we can write like this. Okay, so this molecule is your meso. Okay, you can write these 2 W electron withdrawing group above the plane or below the plane. That's the same thing. Now, second is when you take this diene and taking this trans. Okay, W like this, like this. So you will take trans. So what you get here? Now, what is the product? When you heat it, you will have 6 membered ring like this. So this is 1, 2, 3, 4, AB. So this is your AB. So now at A and B, both the W are at opposite end. Okay, so you can write it above the plane, below the plane means W. Or one more thing. Okay, this is the second. You can write here W. Or here is a W. So these are enantiomers. Okay, plus minus. So cis gives cis, trans gives trans. So this is about the stereoselectivity of the reaction. Okay, now next reaction is, so suppose we have this diene having like this, like this. This is your outside, this is outside, this is inside, this is inside. Not going to add to a dinophile. This. So when you heat it, now you will get 2 isomers. Okay, which 2 isomers I am drawing here? Cyclohexene. तो बनेगा this formed. Then we can take iodine. Is on this. Iodine, I means this inside. O means outside. Okay. So here we have inside, outside, plus opposite of this. Okay, because this carbon is a stereocenter. Okay, so then we can get 2 isomers like inside, this is outside, inside, and here we get outside. Now, according to our stereochemistry, okay, so these 2 products are formed. Outside is outside, outside, both in the same, like outside, outside are below the plane, okay, inside, inside are the above the plane. And then you add in these are the A and B. A and B means here we get a and B. either they are this outside, that may be below the plane or above the plane. Inside may be below the plane or above the plane. So let's take one more example here and to explain it clearly. So this is here is your methyl group, and here is your methyl group. One group is outside, one group is inside. So when you add this ethene to it and heat it, what product you will get? Now cyclohexane, this is formed 1, 2, 3, 4 AB. Okay, this is your AB and this is your 1, 2, 3 and 4. Now the groups present at 1 and 4, they are opposite to each other. So just make it opposite to each other. Like methyl group, like this methyl is above the plane, this methyl is below the plane. So plus minus means this may be opposite. They may be opposite. So next is about the regioselectivity. The most important part of this Diels Alder reaction is about the regioselectivity. Okay, now take an example of this. So suppose we have this diene and we have a D. D means electron donating. D means electron donating group. Okay. So here we have a W. W means electron withdrawing group. D means electron donating. W means electron withdrawing. So when you heat it, what you get here is, so this is your 1, 2, 3, 4, A, B. Take a cyclohexene in here. Okay. So this is 1, 2, 3, 4, A and B. So now find groups attached. Okay. So this D group is outside. Okay. And your W group, which is present in the dienophile, that is your exo. And outside and exo, they are opposite to each other. According to rules, outside, this group is outside, this is exo, they are opposite to each other. So if you make it D, make it like this, means above the plane, then you have to draw this W below the plane, or you can draw it like this, and this make below the plane and this is above the plane. So these two isomers are formed. Now one more possibility is like that. You can take like this, swap it. Okay, this is your A and this is your B. So the product formed are like this. This is diene. Now this is your 1, 2, 3, 4, A and B. Now at 1 we have a D, at 4 we have a W. So then we have to, these outside, okay. So then we have to write here is D and W, plus second possibility is like we have a D and we have a W. So these are these two compounds which are formed. They are at this 1 and this means there is a 1 and 2. These two are the 1,2 products. These two products are 1,2 products. But these two products are, they are 1,3 products. 1, 2 and 3. Actually these are not possible here. These products will not form. Right? So let's take an example to explain it. So suppose we have this methoxyl group, that is electron donating. That's equivalent to D, as the previous example. And we are adding it to double bond CN. CN is your withdrawing group. CN is your withdrawing group. So now we have 1, 2, 3 and 4, A and B. Now which bonds are formed between A1 or 1A, 1 or bond formed between this 1 and A or 1 and B? That's we have to clarify with the mechanism. Okay. Accordingly the product is formed. So like this is formed. Okay. 4 A and B. Now next thing is to where to add these groups. Now in this case we can write it like this: double bond, and we have a C triple bond N. Now this lone pair of oxygen that donate electrons, because due to resonance it's because it's electron donating group overall, and this double bond shift here, this double bond shift here, we get a negative charge on this carbon at number 4. Carbon number 4 get negative charge. Okay. On the dienophile, nitrogen is more electron active than carbon, so electron pair shift here. Okay. This will pull this pi bond here, and this carbon get positive charge. So where the bond is formed? This is here A, this is here B. So bond is formed between 4 and B, or you can say 1 and A. Okay. So this is positive, negative, and this is positive. So bond is formed here. So 4 and B means 4 and B bond is formed. So A is here, and to A CN group is attached. So here we can add a CN group. And to number 1 we add a methoxy. This is your number 1. So this product is formed. Okay. Now in this case, opposite product, like if you say that like this product is formed, that is not possible. Or 1, 2, 3, 4 A, B, like CN here, that is not possible. So this we can say this is about the regioselectivity of the reaction. Like this carbon and this carbon, because of this electron donating group, carbon number 4 get negative charge, and this 4 will attack on B, not on A. Okay, so this opposite structure like A, B here, and A and C, and this structure, this is actually addition of, you can say 1, 3, 1, 2, 3. So 1, 3 is not possible here. Only 1, 2 product is formed. Clear? Got it? So this number 1 carbon, due to the electron donating tendency of this methoxy group, number 4 carbon is always attached to B. So number 4 is attached to B, it means A is attached to 1. So your 1, 2 product is formed. So that is the regioselectivity of the compound. Okay, next one more example. Suppose we have this electron donating group attached to number 2. So same methoxy group now attached to number 2. In the previous example it was attached to number 1. So now suppose we have this structure. Okay. Now what is the expected product in this case? So just write 1, 2, 3, 4 and write here AB. Now what to do here? This lone pair shift here and move here 1 have negative charge. And if you open this structure, you will get this like this C triple bond, and remove electron, it remove electron, positive here. So B get positive. Now in this case, 1 bond with B. Number 1 carbon of diene that bond with B carbon of dienophile. So if we draw this cyclohexene, and this is here 1, 2, 3 and 4. So 1 attached with B. Now this is here B and this is here A. Okay. So at number say 2. At number 2 we have a methoxy here. We have a methoxy group. And at number at A attached there is this cyano group. So now in this case the addition is here like at 2 we have a methoxy group like this here to a methoxy group. So this number 1 carbon, because it is a negative because of this, that bond to B. So 1 bond to B. So at 1, so this is your major product formed. So this is about the regioselectivity of the reaction. So this is all about the Diels Alder reaction, its stereoselectivity and its regioselectivity. So, so in case of this, you can say this regioselectivity, you must see the flow of electron where the bond is formed between, whether the bond is formed between the number 1 carbon of diene with the A of dienophile or number 1 carbon of the diene with the B carbon of the dienophile. Okay, thank you.